Hello, welcome to this video that's covering the AP Statistics 1998 number 6 problem. Be going through the solution of this and talking about it a little bit. This problem starts off by setting up the idea that you are a cultured pearl farm and you have an order for 2 pearls between 7 millimeters and 9 millimeters in diameter. And because you have past experience, you know it's normally distributed with a mean of 8 millimeters and a standard deviation of 2 millimeters. So this is established for you, which is nice. It gives you some place to go. But I can immediately see I'm doing some simulation type stuff because I can see my random digit table down here. So that's kind of in my mind as well. But anyway, let's go through it. So we want to know how many oysters you would expect to open to find 2 pearls of the appropriate size, so between 7 and 9 millimeters. Complete the following parts to design a simulation. So part A, determine the probability of finding a pearl at the appropriate size in an oyster selected at random. So you're just selecting one pearl, one oyster, and hoping the pearl is in between 7 and 9 millimeters. All right, so then they say round it to the nearest tenth. So my first thought is it's a normal distribution. I have a mean of 8 and a standard deviation of 2. So I should be able to find the probability of between 7 and 9. This is a quick, to get the answer is a quick norm CDF on the calculator. But of course, we know we have to write these things up for free responses. So this is what you should do. You should be thinking about what we always talk about and writing out certain pieces, like show a diagram with a label on it. This is a normal curve or normal model with a mean of 8 and a standard deviation of 2. And you can see that here. And I'm interested in between 7 and 9 millimeters. I put a little units on there. That's what I want. I can write the probability out this way, right? The probability between 7 and 9 millimeters. If you're going to use X, though, it's always a good idea to define that X. So size of a randomly selected oyster or pearl. So when you put that into context, you're saying what's the probability that the size of a randomly selected oyster with a pearl in it is between 7 and 9 millimeters, right? So that's always a good thing. They're always looking for z-scores. We always want to know how unusual or not unusual it is. So a z-score for 7 is a negative 1/2, right? We just plug the mean and standard deviation in. Same thing here for 9, mean and standard deviation, and you get a positive 1/2. So negative 1/2 and positive 1/2. I can rewrite my probability, which often we do. The probability that the z-score is between a negative 1/2 and a positive 1/2 is, and then now you can go to your norm CDF. You can put it in this way up here using 8 and 2, or you can put it in with the z-scores and make sure you use 0 and 1. Don't confuse those. Some people mix those up. They try to use 7 and 9, but then they end up using 0 and 1 for their mean and standard deviation. That's not going to work. You're going to get some weird number. All right, so the probability comes out 0.383. I would write this on your paper even though the question stated to round it to the nearest tenth. This I would write down on my paper. Then you can round it accordingly is what they want. So you might be asking, well, aren't we supposed to have a bunch of decimals anyway? Well, there's a reason they wanted you to round this to 0.4, and that's because of the simulation, which we're going to see in just a second. So just do what they tell you, but show your evidence of what you got on your calculator down there anyway, because you're going to need it. Okay, part B, let's see what that has to say. Describe how you would use the table of random digits, which is down here, to carry out a simulation to determine the number of oysters needed to find 2 pearls of the appropriate size. So we don't just want 1. The probability that you already calculated is just 1. We want 2 pearls of the appropriate size. Okay, we could do this in different ways. You're going to find out in Unit 4 that you could do this with a binomial situation. There's different ways that you can get this. And on Part D, you're going to see that we did a simulation, or they do a simulation to kind of talk about that as well. So there's many ways you can do this. For now, we're going to run the simulation using a table of random digits. Okay, so we got to describe these, it says, and then use the table. Using the table to run your simulation, you can see here in Part C, perform your simulation 3 times for part C. Okay, so you'll see that on part B, I identified what I'm going to let my numbers be. So I said let 1 through 4 represent a pearl of size between 7 and 9 millimeters. So why am I doing that? Well, because we had in the previous step, we had 0.4, 40% as our probability of randomly selecting that pearl. So if I go 1 through 4, that's going to be 40% as well. So I'm matching the percent up to the numbers. Let 0 through 5, 0 and 5 through 9 represent pearls that are not appropriate sizes. So that's going to be 60% not appropriate, 40% appropriate, right? So this gives the probability of choosing an appropriate pearl size equal to 40%. You need to tell them how you're running the table. And maybe this you could write in part C, that's totally fine, because they said run the simulation in part C, but I started writing it anyway because I knew that was coming. So I will start at the top left and move horizontally on the given random digit table. You need to tell them this. Where are you starting? And then how are you moving? Are you going vertical? Are you going horizontal? Are you going every other number? Are you taking one number at a time? Are you taking two numbers? You should be telling them this kind of thing. You also need to tell them what your markings mean. So I said X is a bad size and an O is a good size. And I will continue until I get, you got to tell them like what a trial represents. That's the next piece. I will continue until I get 2 good pearls and then start another trial. So whenever you end up getting 2 good pearls, that trial is over and then you're going to start your next trial. And I said, see the table. So let's look at the table. This is actually part C now because it says run your trial. So actually, let me go back here real quick. You'll see on part C that I put my results in here, right? So that comes after. But here's the work. So running a trial, I just put in zeros and X's, right? O's and X's. So yes, that's 1 to 4. No, no. Yes, that's 1 to 4. That I got 2 pearls, so that's the end of my trial. So I put that vertical line in there, and I call that trial 1. Then you continue where you left off. No, 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 no. And then I end up with a 3 and a 2. A 3 is 1 to 4, and a 2 is 1 to 4. So those are 2 pearls of appropriate sizes. So it took me that many times to get those 2 appropriate pearls. Trial number 2. Trial number 3. X, 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 and then I got an O, an X, and an O. As soon as I get my 2 O's, I'm done with that trial. So I've run 3 trials where I got 2 pearls of the appropriate size, and then you want to talk about your results. Whether they ask for it or not, you should be writing it down. So on the first one, it took me 4 tries in order to get 2 pearls that were okay. This 1, 2, 3, 4, 5, 6, 7, 8. On this one, it took me 8 oysters in order to get 2 pearls of the appropriate size. And on this one, it took me 1, 2, 3, 4, 5, 6. It took 6 oysters to get 2 pearls of the appropriate size. So I will put those results down. Trial 1, results. Trial 2. I said pearls, but you could have said oysters, right? Okay, and to show that. Now, I always kind of, what's the mean of that? I always give a center, like what's the median and what's the mean? What's the center of that? So it would have gotten six oysters or 6 pearls in order to find 2 good ones, right? So that's part C. Let's flip this over, look at part D. On part D, they say, okay, let's now, instead of doing the trial just 3 times, we're going to do just what you did, but we're going to do it 100 times. And in addition to that, not only are we going to do it for 7 to 9 millimeters, but we're going to run it for 4 to 6.5 millimeters. Well, my mind is immediately going, all right, I've already done some work for the 7 to 9 millimeters. I already know kind of an idea like what oops, let me go up here. I kind of know already what the probability of choosing something between 7 and 9 is. It's about 38.3%, so 383 or rounded to 4. I haven't done that for the other one yet. So, but again, this is just the probability of randomly selecting 1 pearl, we still would need to calculate the probability of getting 2. And then they also, like what you're looking at on these histograms, you're looking at how many oysters it takes to get 2 of those, given that the probability of getting 1 is one of these. So there's a lot going on here. At first glance, like people kind of jump in and they go, oh, I'm just going to count up between 7 and 9. It's like, no, you're totally misinterpreting what you see in front of you. This is the number of oysters that this is not the size of the pearl. Like, it's confusing to say like, oh, this is 7 to 9 millimeters is a good pearl. That's different than what you're seeing here. This is how many oysters did you have to open in order to get 2 good pearls of that size, right? So a totally different animal here. That's what you're doing in the simulation though, right? So it is similar, or it's the same thing as what you were doing on your simulation. I just know that I don't have the 4 to 6.5 millimeter simulation yet. I don't have probability of that. I don't have any of that yet, right? But what they're saying is then, they haven't asked a question yet. They're just setting this up. Let's go to the bottom here. So identify which distribution, A or B, represents the search for 2 7 to 9 millimeter pearls. Explain your reasoning. Right. So at first glance, you might be thinking, well, it's going to be, something like 40%, or all kinds of stuff might be going through your head, but you really have to go down, like really break it down into, how do I come up with a center, or know what my distribution would look like? And in this case, the best way to identify this is to know what is the center going to be for this situation, from the 7 to 9 millimeter situation, right? So where is that center? What do I expect? So this brings up what we call expected value, right? What's the expected value? How many oysters am I going to need to open on average in order to get 2 pearls of 7 to 9 millimeter size, right? So how am I going to get that? What's the expected value? That's the whole center of this, expected value, expected value. All right, so let's go look what I did here. This is a lesson in don't cram things in the margin. I started writing thinking I had enough room, and then I started running out of room, and I still continued. I did what I tell my students not to do, and crammed it in here. So it's a little uneven, and it doesn't, it's not nice, complete sentences the way it really should be. But here's how it works, right? So since we know the probability is 0.383 or 0.4, to get expected value of that probability, you would take 1 divided by that probability. And this is something we're going to cover probability in Unit 4. So maybe we're getting a little ahead of ourselves. But this will give you the expected value. Just think about if you roll a dice, and you have 6 options on a dice, right? So the probability of rolling a dice and getting any side, like let's say I want to get a 5 and I roll the dice, the probability is 1 out of 6. So if I reverse it on you and I say, how many rolls do you need to have in order to get 1 5? Well, you would say, well, you just have to roll 6 times on average in order to get 1 5, right? In order to kind of be guaranteed you're going to get that 1 5. If I roll it 6 times, it's not really guaranteed, but I have a high probability. So it's the same thing no matter what you're doing. If I flip a coin, so if I take 1 divided by a half, because there's a half of a chance of getting tails and a half of a chance of getting heads, so 1 divided by a half would actually end up being 2, which means I have to flip the coin twice in order to get a heads once. Same thing on the dice. You take 1 divided by the probability, so 1 divided by 1/6, and you would end up with 6, right? 1 divided by 1/6 is 6. 1 divided by 1/2 is 2. So whenever you take 1 divided by the probability of something, you'll get the expected value. Like how many times is it going to take before you expect to get what you were looking for? So you do the same thing up here and you say, okay, to get 1 pearl of the correct size was a probability of about 40%. So if I take 1 divided by that number, that will give me the expected value of getting 1 pearl of the right size. So this would come out to 2.5. So I would have to open up, on average, 2.5 pearls in order to get one, or 2.5 oysters in order to get one pearl of the correct size. So in order to get 2 of those, I would just double that. So I would have to open up 5 oysters in order to get 2 pearls of the correct size on average, right? So that's what I was trying to get across here. You divide, multiply by 2, and that gives you the expected value of getting 2 pearls of the correct size. Now we did have the 0.383 up above, so if you didn't use 0.4 and you use 0.38 or 383, that's okay. You do the same thing, and that will give you 5.26. Very similar to 5, right? So you're kind of in the right ballpark. But that is the expected value. So that's what you're looking for on your table or on your bar charts here, right? You're trying to say, okay, what's that expected value? So it should be about 5. The center of this distribution, since it's skewed to the right a little bit, would be a little bit to the right over here, right? So it is right about 5. If I look at this other distribution, the center of this, kind of the medium, would be in here, but it's going to be pulled to the right because it's skewed to the right. So that might be over here like at 8 or 9 even, maybe. At least 7. You're going to have a center of more than 7 for sure. So this distribution matches a center of about 5 a lot better. So distribution A is the one that matches the 40%, the one with the 7 to 9 pearls. So that's what I would be trying to get across here. This would match, distribution A matches the probability of selecting a pearl between 7 and 9 because we have the expected value of about 5. So that matches the mean, or matches the center of the distribution of A, yeah? If you do the work on the other one, which once you've identified this, I'm not sure you really have to. Yeah, I don't think you really have to. But if you did the work on the other one, you get the probability in between 4 and 6.5 instead of 7 to 9, and that gives you 0.203. You do the same thing. 1 divided by 0.2 gives you expected value. Multiplied by 2 will give you like 9.8, right? So if you go back here, then you're going, okay, I would expect to have to open up about 9 or 10 oysters in order to get 2 of them, to get 2 pearls that were between 4 and 6.5. So I would have to open up this many pearls, right? Or this many oysters, which matches this distribution. It wouldn't make sense over here, right? This is definitely not the center of this distribution. It's the center of this one. Okay, so distribution A is your answer on that. We still have one more part. Part E. Use the appropriate distribution, so for us that's distribution A, to compute an estimate of the expected number of oysters. Open to find 2 pearls between 7 and 9. So we've already established that it's about 5 for the number of oysters you would have to open up. So we could kind of estimate that, about 5. You can use, like, you could just look at it, right, and say, oh, it's about 5, maybe a little more because of the skewness, but it's about 5, definitely more than 4. So right about 5. You can estimate it. That's okay. It's better to calculate it, which we've already done one of the ways to calculate it. So you could come up with a 5.26 using the 1 over the 0.38 method, and then times 2. You could do that method and come up with a value. I did a third method on the back here to show you what that looks like. I'll try to make sense of that for you. Can I show both of these at once? Sorry. I don't know if it's going to fit here. Okay, I'll do my best. All right, so what I did is, you're looking for, this is another way to calculate expected value, which we're going to be doing in chapter 4 when we do probability. But the whole idea is that there's 100 of these simulations, so I'm going to do a weighted probability. So you're saying to get 2 good pearls out of 2 oysters, there was a 9% of the time that happened. So I took 2 times 0.09. And then to get 2 good pearls out of 3 oysters, that happened 22% of the time. So I took 3 times 0.22. This is a weighted average. All these little decimals will add up to 100%, and you're multiplying each one of those times its own, the value that it represents. right? So, and then you add them all up. So then we're taking to get two good pearls out of four oysters. That happens 20% of the time, et cetera, et cetera, et cetera. And you go through all of those, and when you get done, you add them all up, and you'll get 5.16, which is very close to our estimation of 5, which was also very close to our calculation of 5.26. So any way you do it, you're getting right around 5. You got to have a method, though. You really do. For the estimation, you might want to use the median, and then maybe kind of talk about how it's skewed, something like that. This is showing your work, obviously, and also this is showing your work. So any of those would probably work. I know everybody wants to just go to this one because it's easiest, but if you really want to, get your high marks and always be sure that you're, using statistics to come up with your proof, then you should come up with a method, some kind of calculation method to do it. That's what I recommend. All right, that's a number 6. So, it's an involved problem. It involves some probability, it involves some z-score work. There's a lot going on there. It involves a simulation, right? Using a table, random digit table. So there is a lot going on there, but that's expected because it's a question number 6. You should have about 20 minutes, 20, even 25 minutes to do a problem like that. So you should expect that kind of work. Yeah. All right. Thank you very much.